Hello and welcome to VitoshAcademy. In this short video I will show you a bit about Perlin noise and random noise with Jupyter Notebook. So pretty much not wasting time but starting. We just have three imports that are really kind of what we would be using in this video, and then I will try to explain really in short what is noise that is plotted pretty much when we have random numbers. We would get something like this. You see the purple, white, blue part of the square, and when we have Perlin noise, the end deliverable of the video, we would have something beautiful as this one thing here. Our research questions for this article that I'm presenting is how to build Perlin noise in Python, pretty much the important part, and then how to distinguish random noise from Perlin noise. Just a really simple method is going to be shown pretty much. So let's think, what exactly are we presenting? What is content generation through algorithms? What does it mean? Let's take a look. Let's say that we have this example, and with this example we will try to make this square. So I'll press A in order to generate this one, and I'll write this example. Then if I press A again, or B, and I write example here, this is what I'll do. And if I want to use the plot noise, pretty much this one, I can say, okay, I want to plot the example. So just to see what's going on. And as usual, it never works like this. Okay, plot title, okay, example, or 2 by 2. Yeah, so what did we just generate it? We have 1 0 0 1. So 1 is the white one, 0 is obviously the black one, and then 0 1. If we want to make it a bit more interesting, we can make it like this and see what's going on. Okay, 1 0 1 1 0 1. So 1 1, the white one, 0 0, and then 1 1. So this is how we pretty much plot noise. This is the idea of plotting random numbers into a graph, and this is what we're going to do with Perlin noise. Just to make it a bit more interesting, here I'll write 0 here, 1 here, and yeah, 1 here. So this way it would be a bit more interesting, and it will not be 2 by 2, but it will be 3 by 2. Yes. So this is what we would be building. Okay, this is obviously not random, and whether it looks nice or not, it's up to you. It's 3 by 3, so we can make it a bit more interesting here. Write 0.5 here, we can write 0.3. Take a look, you see it's a bit gray. Yeah, why not? Definitely interesting. We were using this plot noise function in order to show this. Pretty much what it takes the noise, the plot title, and the given CMap. We have other CMaps that we can pretty much take. I'll just take Twilight here, and if I go here and I pass it, you probably saw that it became a bit more interesting with other type of numbers. Yeah, why not? I'll still use the gray one that I had before, the default one written here. We can put also the color bar of the function. Let's see how it will look like. Yep, like this. And if we want to have some non-random noise based on this matrix here, this is what we're going to do. Strange 6 by 6 chess. This is pretty much what I wrote. If we want some random noise for the one here, what we can do is the following. For the random noise, this is some function saying generate random noise here. I mean, I'm just going to press not A but B. B is the shortcut for creating a new cell here. And the moment I ask generate random noise, and I say 3 by 3, I'm going to get some random coming from np random range with height, and this is how it is going to be. Yeah, 3 by 3. And then if I say okay, make some random noise function, and I give some size, it would be plotted. So what I can do is say okay, make some random noise, and then as size I give 3, and as label I give some random noise. What is going to happen now is this make random noise function would take the size, would assign it to the width and to the height, so it's a square, and it would call random noise function, generate random noise function from here. It would give us pretty much random stuff here, and then we will plot the noise. Yeah, not bad. And it would be white and black because in the plot noise we would be using CMap given, which is usually gray. Let's take a look how it will look like. Okay, let's try again because it's not defined. Okay, make random noise, make some random noise. Okay, make some is not defined, so the name of the function is a bit different. It's like this. And if we say that we are not into this, let me see whether I will be able to write twill light correctly. Not, of course. Should have been like this. Okay, make some random noise here in the function. I'll write twill light. So and I should activate the function as well. Now the twill light effect should appear. Yes, this is obviously something random. That's what I wanted to show. Yeah, random as random can go, I guess. So what is interesting about this random noise, and how do we understand that this is random noise and not the nice looking Perlin noise? I mean, the nice looking Perlin noise is here where we have the patterns, and here we don't have any patterns at all. We simply have 10,000 is a bit more, but yeah, we have this. So a way to understand really that this is a random noise is pretty much if we open Paint. It's a really interesting way of understanding, but it works. If we do the following, the snipping tool, we copy it a bit and we put it in Paint, then what would be interesting is that if we resize here and we move the resized thing and then we put it back, we wouldn't see any change of the patterns. No. And if we do the same with the Perlin noise, literally the same exercise, like this, we put it into Paint, we copy and move it, you see, it's obvious that something around here, here, there, and there has happened. Probably if I zoom a bit more, you will be able to see the difference in the squares here. It's obvious something's wrong. So this is a good way to say, okay, this is a random noise and this is a Perlin noise. So going further with this one, we would generate this interesting 10 by 10,000 by 10,000 random noise that I already did. Here I am explaining in the article what I have already showed you, that it's a bit impossible to say where the square starts and where the square ends. And now the Perlin noise methodology is going to be explained pretty much step by step. First, we create an empty noise array. Okay, first thing first, create an empty noise array. This is how it looks like from the function. Okay, noise. I already gave, I guess, some values of width, height, and width, but in this case, I'll give it again. Height would be, let's say, 20. Width would be also 20. So this is how the thing looks like. So create empty noise array. Yes, this is how it is. Then generate random gradient vectors. Yeah, just pressing this, so this disappears from our function. Gradient vectors, mp random height divided by scale plus 2, width divided by scale plus 2, and it's a two-dimensional vector, so we have a 2 after the comma. Yeah, what is exactly the scale? The scale is pretty much the value that we use in order to divide the tiny squares that we are using. Let me show a bit more with one of the paint pictures. If I can open paint once again. Yeah. So to generate the random noise, I'll take one of the already pre-generated examples in order to try to show what's happening. Okay, this is it. So this example has been generated with 256 pixels by 256 pixels with a scale of 10. So pretty much it will mean that we have the following number of squares like this, 225 squares here. So it's like this. And we have 256 pixels. Each square is of 10. So we have 10 by 10 squares here. So in general, the total number of squares that we would be looking at would be something like 225.6 squares times 25.6 squares. So this is around 625 something. So the idea how to do this beauty here is the following. Each one of those is generated separately, but the tricky part is that we are doing them in a way that when we go to the next square, we don't see this difference. So that's pretty much the whole magic. So generate random gradient vectors. Great, we generate those random gradient vectors, and then we start looping through the array. We loop in the examples that I have shown 256 times 256 times. It's not a lot, but it's interesting. And we calculate the position of each pixel. So 256 pixels on the X, 256 pixels on the Y, and then we calculate the position of this pixel as fractional offset from the position of the edge of that cell that we are interested in. I hope you're still following with me. So let's take a look at some of the things in this function. Pretty much this is the function. What I'll do now is I'll put a print here, cell hit and print, so we get just to see what's going on. And I'll change this from 25.6 to 12, yeah, to this one, see what's going on, and of course run this and run this once more. So the first pixels are with zeros, then 0, 1, 0, 2, and we continue with the position. This is how the Perlin noise example looks like when our width and height is 25 by 25. Okay, here it's a bit visible that we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, obviously it's 25 and a bit more, because no, it's 25, not 25 and a bit more. So it's 0, 20 and 25, and 0 there to 25. Yeah, so I put a print somewhere here. And what is really important is that, okay, it's obviously pixelized, this example, not the best one, but still you see that the colors are kind of transferring from one to the other without being able to stop. Okay, I can do it like 10 by 10, scale of 25 of 10. So we literally have 10 by x, 10 by y, and yet you see it's kind of beautiful also. Yeah. Okay, scale of 1 would be interesting. Okay, that was unexpected, but actually, if I have to think about it. Okay, 100 and scale of 1. Yeah. The idea is just to have pretty much scale of 1 is obviously something strange. So 100 tiny squares, and each tiny square has 10 pixels in it, 10 by 10, so 100. So let's try to continue with whatever try to explain. Cell offset X and cell offset Y. Let me see which one I try to print. I'm not seeing the print. No. No, the print was removed, so I'll write the print once more. Print cell offset X and cell offset Y. So it's on the same line. And then I have to finish this thing here. And I have to write it just once. Yeah. So these are the offsets from the corresponding corner, because it's an offset. Yeah. Okay, so calculate the dot product between gradients and offset. Pretty much the idea with these dot products is what makes the Perlin noise fancy. So we are using dot product top left, dot product top right, dot product bottom left, and dot product bottom right. I'll show once again. Just thinking. Okay, probably if I use it like this. Okay, let's say 250 by 250 by 10. And I'll have to remove the prints. So what is really important here is back when we have those squares in which we are interested. Red pen, for example, this one. In order to calculate, we put those random vectors and we calculate a dot product based on the random vector. Okay. And the offset of the pixel. The offset of the pixel like this. And yeah, this is what happens here. So interpolate the dot products using smooth step function. This is something interesting actually. Let's see what will happen if we force this smooth step function to return 1 and not what it's currently returning. See, obviously we received something strange. At the end, our tiny squares are beautiful, but the visible distance here is not okay. So let's give it a bit more of an example. This would require some seconds for my PC. I hope. It was more like a minute. It's good that I actually finished the video, put on pause. So yeah, you see the borders are visible. I'll just make it like this and I'll uncomment the return 1 with the smooth step. And now we have this beautiful example here. So question, what exactly is this smooth step doing? That's a good question. And the answer of this question would be done through a bit of research. I'm going to write smooth step function in Google and show what are the results. You see, this is how the function would look like everywhere. It's really smoothing everything. Yeah. And this is how the smooth step function would return based on whatever we give it. So smooth step, let's say 0.5, it returns 0.5. 0.12, it returns something interesting. So what the idea of the smooth step is, based on the function that you saw, is that it actually creates a nice gradual transition from the starting point to the destination. Let's say we get 1, it returns 1, of course. We get 0, it returns 0. That's because of its function that was pretty much like this. Yeah. It really makes the transition gradual. So also another really important part with this function is that in the context of Perlin noise, what it does is actually it helps you to interpolate the values between the points in the grid cell. We're only working with 1 and 0. I mean, somewhere here I'm doing it only, yeah. Normalize the noise values within the range of 0 and 1. Yeah, it's a fancy formula here. Okay. So that's the idea of the smooth step. Without it, we wouldn't be having this beauty, we would be having that ugly squares. So continuing, I'm just going to remove the prints. Oh, they are already removed. Cool. LERP is linear interpolation between two values. I am doing it here. The interpolated top, interpolated bottom, interpolated value with some weight. Now the interesting part where we actually generate the Perlin noise. I'll leave it 256, 256.10 as it was in the beginning. And see how it looks like. Something interesting with Python is that we have like a whole map of supported CMAP values. This is how they look: accent, accent R, blues, blues R. I mean, I'm just going to put spectral, spectral R, and what else? No, I'm going to put this tree. Let's see how they are going to look like. So, yeah. So for CMAP in supported map, I mean, I'm just looping through these three values. I am plotting the noise, naming my graph with the name of the CMAP, with the string of the CMAP, and I'm giving the CMAP. So this is how it looks like. You see, we have some green places here, same green is red here. And pretty much we can put it also here. Yeah. So pretty much that's all I wanted to show about Perlin noise and the algorithm I'm using, made from Perlin, the guy who invented it, and get an Oscar for it. Something funny else, something else about this. I wrote some tests here, so let's see. Yeah, the test passed. I mean, if they were not passed, let's see. -1, for example. No, it's always bigger than -1, so just to see, this is like exactly an option saying what happened, why the test didn't pass. So that's pretty much everything. Thanks for bearing with me for around 30 minutes. Enjoy my YouTube channel and have a great day.